Welcome to Study Loop.
So once again, we have a block. So uh, we're given a surface and a block. We want to think of it as a frictional surface, and there's a block sitting on right there. Um, the the mass of the block happens to be 15 kilograms. So there's a spring attached to the block, and the mass of the block happens to be 15 kilograms, like that. Or what we can say 15.0 kilograms. And the other thing that's happening is that there is a ball that's moving towards the block, and the mass of the ball um, happens to be um, the well, it's gonna be struck by a stone. So this is a stone, and the mass of the stone happens to be 3 kilograms. The stone is moving with an initial velocity towards the right, which is positive, and that initial velocity um, happens to be the stone is going to go, it's going towards the right, and it's traveling at a horizontal velocity of 8 meters per second. That's to the right. The initial velocity of the block, as you can see, is 0 meters per second because it's not moving. Um, the stone is going to bounce back. So at some point, this is kind of like what's happening before. And then what's happening afterwards, uh, this the block is going to collide with the not the block, but the stone will collide with the block. And obviously, you see what's going to happen when there's a collision. It's going to be a push. So we still have the same scenario like that, but this time something new has happened. The stone has collided with the block, and there is a movement. Okay, so if you think about this, there is a movement. There's a maximum distance of compression x, and that's what we want to find out. We want to find x. Remember, the ball is bouncing off, so the ball is going to bounce off that way with the final velocity. Not the ball, but the stone. The stone will bounce off with a final velocity that happens to be 2 meters per second. I mean, you could say -2 because it's moving towards the left right now. And the block itself, as you can see, is moving towards the right with a final velocity of we don't know, but we can always determine that. So two types of laws that we're using in this particular problem. The first one is the law of conservation uh, of energy, and then the second one is obviously the law of momentum, conservation of momentum. Okay, we're going to start with the law of conservation of momentum, which says that the initial momentum equals to the final momentum. The initial momentum of the system is ms vsi. That's the momentum of the stone, the initial, plus the initial momentum of the block, and that's going to be equal to the final momentum of the stone plus the final, this is the stone, plus the final momentum of the block. Okay, so that's what we have in this problem. We have the numbers we need. 8 meters per second. Remember, that's the initial velocity of the block, of the stone. Sorry. And so we want to solve for the final velocity of the block. You know, moving things around, you get to see that the final velocity of the block becomes equal to the initial velocity of the block is 0, so this whole thing will be 0. So then we have the initial momentum of the stone minus the final momentum of the stone. This one, when it moves to the left, becomes negative over the mass of the block. Okay, so that's that's kind of what we have in terms of simplifying this problem. In the next page, we can show the the final simplification steps. So the final velocity of the block becomes equivalent to, going back to the formula, mass of stone. We can pull out that, and then we're left with the initial velocity of the stone minus the final velocity of the stone over the mass of the block. So the mass of the stone is 3 kilograms times mass of the block, or rather initial velocity of the stone is 8 meters per second. Final velocity of the stone is -2 meters per second, and you can see that from the other side. This is -2 meters per second, and then you want to divide that by the mass of the block, and that's 15 kilograms. 15 kilograms. And so, the final velocity, which is a step in helping us get the distance x for the block, is 2 meters per second. If you go back, our goal was to find that distance. So this time round, in the next page, we're going to use the law of conservation of energy, which means that, and this time it's focused on the spring itself. The spring is the spring has elastic potential energy, and the block has kinetic energy. Remember, the initial kinetic energy of the block is 0, so we don't even have to think about that. So the final, this is the final kinetic energy of the block. So the final kinetic energy of the block has to be the same as the elastic potential energy of the spring, and that's what we're looking for. And so, 1/2 mass of block, final velocity of block squared equals to 1/2 k x squared. Something else we also have to remember is that we're given the spring constant for the block, and the spring constant happens to be 500 newtons per meter. And so if we go back, we have that number. We're trying to solve for x. We can divide both sides by 1/2 k. 1/2 k. The halves cancel, and the k's cancel on this side, and so we have x squared equals to mass of block and final velocity of block. And so over k. And so the value of x is the radical of mass of block, final velocity of block, squared all over k. The other thing that happens is now we can plug in the numbers. So 15 kilograms times final velocity of block, we found 2 meters per second. We have to square that over 500 Newton meter. So, going back to using a calculator, we'll see that this is radical 15 times 2 squared. Close that. Well, actually, you gotta go back and do divide by 500. Then close that. It's giving us that. 15 times 2 squared divided by 500. And that gives us 0.346. That's the distance, x is 0.346 meters. So, once again, we use the law of conservation of momentum and the law of conservation of energy. The first step was to find the final velocity of the block, and that happens to be 2 meters per second. And then we use that together with the law of conservation of energy to compare the kinetic energy of the block and the elastic potential energy of the spring, helping us solve for the distance x. Hope you enjoyed the video. Feel free to ask any questions and have a wonderful day. Okay, thanks. Bye.